Yeah. Classes are you taking this semester? Nothing. Is it a 7-step program or something? No?
Well, I've got a 12-step program for ice cream and chocolate.
Oh, okay. Classes too. What? I was thinking classes too. First you just audit a few, to withdraw, just audit a couple.
Well,
They give me a schedule I like. I'm pretty practical about it.
still out. Your body's fine?
Yeah, it's all right. Good. I'm getting older and I can't do as much. Yeah, I know.
It'll be fun when you guys.
But I can't tell if it's due to, wear and tear or issue like that.
Oh, the muscle degeneration starts in the 60s.
Yep.
And then the carbon dioxide is getting worse every year.
And there you are. Yeah, but I'm not quite 60 yet. And, definitely. Exercising more and more. Getting less and less back. Except the soreness. The soreness. That's certainly a good thought.
Scan the article.
The problem is the time to leave. Why retirement? That's what you said. You get that. No, but I will retire. You can't just scan. No, it's very. I mean, that's what.
You can come sit over there with us if you want. Okay.
Yeah. Well, yeah. It's harder there. It's critically important because that's about the best science can do, actually, as it turns out. Yeah, so everybody claims they found something.
Too much sugar.
Hey, how's it going?
Yeah. That's a natural. Somebody when I was undergraduate, every article you read will show you their typical payment. What they really mean is their very best run. Yeah. There's typical data and everything's just smooth. It was 1 out of 46 data. And one's had errors here and there. The team has completely collapsed and stopped taking data.
Do you need me to turn in my notes or anything, or
What's
just?
your name? Yeah,
They
yeah.
had a dragon biologist explain.
I know your name.
There you go. Oh, so I need to. I didn't.
No, I know.
Oh, you know? Okay.
Yeah, yeah. I put.
Oh, excellent. Thank you.
The other one had some physical problems. And then he's not, let's just say he's not as smart as but when he works, he's real.
I'm scared.
I have a real location. Yeah, he's a good guy. He doesn't have the words of brilliance of Terry. Terry, after a year, was telling his professors that he was wrong. He was right. Often that leads to never getting a Ph.D. as you're going out. So he also managed to negotiate. Pretty good.
Today we have a speaker who will a long trip from north of our world, from Alaska. His name is Alexei Rybkin. Alexei Rybkin, to be precise. And the University of Alaska Fairbanks is his place where he's professor of mathematics in the Department of Mathematics for maybe second decade.
15 years. All right. Well, it's a pleasure to speak here. You can sit closely if you want. It's a pleasure to have such a big audience. And I'm going to talk about two huge subjects of mathematics, physics, applied mathematics, and all kinds of applied sciences. And as you can see, the title is actually a question. What do tsunami waves and quantum mechanics have in common? This question needs to be answered at the end. So I will give you all kinds of hints what the answer is. And you don't have to know much about either object or subject to actually answer this question. Just common sense. All right? And I'm from Alaska, and people always ask me all kinds of questions, what life in Alaska looks like, and all that. And I developed over years a habit to put a few slides related to Alaska. And that's what the first one is. This slide, this picture was taken last fall, not last fall, late August, but not 2013, 2012, and it's a rainfall. And that actually picture made it to our local television. It's a good one taken in Tsunami National Park. It's a place which you want to visit one day. And here's something related to my talk. It's how tsunamis are actually created. This is a glacier, and what it does, it calves ice. So huge chunks of ice drop down to the river, producing tsunami waves like this one. And you know how destructive those waves could be. This one was not but potentially they could. And like I said, I'm going to relate to different objects, and so I'll give you some history behind each. And the first part will be about the equation which actually describes tsunami waves. It's one of the models, so-called the Ph.D. equation. And everything started from a famous discovery by John Scott Russell, who was first to pay attention to something which we now call solid, which particular example is tsunami wave. And there is a very interesting history behind this man who was not a mathematician, was actually an engineer, pretty successful engineer. And then he discovered the solid, and he switched his interest to studying solidons. And as a result, he actually died pretty poor. And not recognized during his time. But now everyone who studies integral systems from Ph.D. knows this name. Okay.
Yeah, there's another picture of Alec Park.
There's a polar bear standing next to the apron. It's basically the way I look at it.
Oh.
Let me reload this thing. Oh. It was working, trust me.
It was great.
We checked.
The rest was redacted by the NSA.
Does anybody have any idea what the problem might be? Yes, no, it's not.
Is there a slide sorter view?
Huh?
In PowerPoint, there's a slide sorter view. You could go to that and then click on the next slide instead of trying to advance one.
And how to do that? And actually,
Keep going. Slide down the thing on the right. Slide down until you find slides again. There we go. Keep
No,
going.
it's-
Pulling it.
Keep going.
No,
Keep going. There'll be some down there. There. See, there's one.
yeah.
Trivial solution.
Well, I can't jump to slide number 8.
That's 9. Keep going. Hit down. Hit the down arrow there on the top.
Yeah,
You
okay.
keep going until you get somewhere. Yeah. There you go. It thinks there's 67 pages, and I thought there were only 35. It was very
Recompile it.
recompile it. Yeah.
Keep going down.
No,
we're finished.
There's nothing on that.
Close it.
It's dead.
Yeah, let me try to open this one. Okay, this one,
Good.
no. So, what he discovered, he wrote a manuscript about it, and now here I cut and paste what many books do, and I believe in the Salatin community is something people should remember by heart. It's where this theory started. And I give you a minute to read it. If you don't want to, there will be next slide which explains what he saw. It's a nice old English. No.
Okay.
All right, well, now it's what he saw. Back in 1995, there was a conference in Edinburgh on solid waves, and they actually reproduced what Scott Russell saw. And using a boat, they didn't have the same type of boat, but any boat would do it. And you see what actually happening here. This boat produced a heap of water in front of it, and then they actually stopped. But this heap of water, you see how right shape it has, and would keep on going, and for, as a matter of fact, for a couple miles, unless it got lost in multiple windings in the canal. So this is what Scott Russell noticed back then and was fascinated with that, and he instantly saw that it's not an ordinary wave. And but Bernoulli and Newton and their theory of waves did not support the existence of such waves. So that is why Airy, who was the biggest authority on waves, didn't actually recognize Russell's work and said it can't happen. And Airy, of course, is well known nowadays. Airy function, you might have heard that one. And but he couldn't recognize the existence of solitary waves, or couldn't recognize the importance of those waves. And so he got so fascinated that he decided to investigate what he actually saw. And here's an animation produced a good friend of mine, and she's actually not mathematician, she's a computer art professor, and she produces the animation for me. Let me see how it works.
That will work if you pick up the file from the desktop. You'll take it from
Yeah,
flash and on this here,
yeah.
as we checked.
Yeah, that's
Unfortunately, we cannot see animation now.
yeah.
From the desktop.
That's too bad. Let me now mess around with it. All the files actually here. you know, by some reason doesn't react contra escape. So, huh? Or just escape. Okay, okay, let me. Okay. Oh. You see, that's what he did. He installed, put a huge tank in his backyard, and he would start reproducing what he saw by dropping different blocks and seeing, trying to recreate what he saw in a lab situation. And and he did quite a bit of research, and he spent 12 years messing around with this pool. And what he, that is previous one. What he's found out is that this wave is extremely stable, and so it doesn't flare out or something, doesn't change the shape unless it hits the other end of the pool. And what else he found out is the velocity of this wave. And it is something we still use to calculate the velocity of a tsunami wave. Its square is g, gravitational acceleration due to gravity, times the total height, the height of the pool plus the height of the hump. So, so the velocity depends on the height. The higher a wave moves faster, and it's well known in the tsunami business. And they never merge. And what also interesting he found is that if he drops a really big chunk, then it would produce two solids. One would be bigger than the other, and of course the bigger one would run faster. And when the big one actually overpass the small one, it doesn't observe the small one as if they were totally different, totally linear objects moving independently. And it's a lot, so he discovered a lot. And one more experiment he did, and it's a question. Can you guess that if it's realistic? Oh, this, sorry, it's actually the next slide. I'm really sorry. It picked up on a picture by some reason. So what she tried to do, she tried to play with similar situations, similar experiment into a bathtub while creating these pictures. And when she did, she removed something from the water and tried to see if it's going to produce a trough, yeah, they call it trough, which would move same way as a pump. And she thought it would, but it was just an error in her experiment. That's what this the next slide was about. By some reason, it picks up the wrong picture. And the next, of course, he tried to write up some papers on his research and wrote pretty long report on waves, and where he would explain everything and trying to get some recognition. Do you know how many times during his life that report was cited? 2 times. And And he was really frustrated about it, and they didn't do much anymore since then. That's why he died poor. And of course, he will be remembered not for what he did before, but what he did in his backyard. And today his discovery is used every day, and you can notice it, that communication, fiber optic communications is based upon solitons. Those waves, but in optics, are used to carry over information. Their stability and non-interaction with each other is the reason why we are able to move that much information at the same time without interfering in the piece of information. It's all based upon his discovery. And now it's a kind of commercial break. It's another picture taken on the same trip to watch the ice calving. It's a light here, so you can see it, but it's an eagle, bald eagle flying. All right. Well, and the next step. Everyone forgot about his discovery, and only 2 people actually recalled his discovery. But in 50 years, so they derived the equation which bear their names, and which actually describes what Russell saw. And those names are Didier Cartlet and Gustave de Vries. And Didier Cartlet was a famous mathematician, and Gustave de Vries was his student, Ph.D. student, who actually never did research after he chose a high school teacher career. And in his dissertation, they derived the following equation. And it's complicated, but if you rescale all these physical quantities, then it can be written down in a very simple way. You can even rescale the 6 if you want to. So it has 3 pieces, and subscript stands for partial derivative. So it's what we call now Cartlet-de-Vries equation, and it's non-linear equation. It has second-order linearity, and x is a spatial variable, runs from minus to plus infinity, and t is positive. And so to solve this equation, we impose what we call initial condition, which is also called initial profile. But it was 50 years after, and even then, no one recognized their work. And when de Vries died in 1941, this work was not cited in his obituary. So this equation was ignored. It was not called Cartlet-de Vries equation. And so they didn't get recognition for it during their lifetime. And now let's just consider this equation. Let's do some simple mathematics to see if we can understand the structure. So if we drop the nonlinear term and consider what we call a linearized equation, which is also called area, the same area which didn't recognize Russell's work, then this equation can be easily solved by Fourier. And it's what we call dispersive equation, and the solution can be written down in this Fourier form. And the solution doesn't look interesting. So if you take as initial profile here that initial pump produced by the drop plot, you will not see the effect. It will be totally different. Wrinkles of water, nothing particularly exciting. But on the other hand, drop the third derivative from the equation and consider the nonlinear part, which is also, I think, called Berger equation, that one has a drastically different type of solution. And one can check by inspection that this would be a solution to this equation. So it's, of course, implicitly defined function, but can be easily analyzed. If you remember studying a wave equation, probably you see that this is nothing but a propagating wave with velocity 6u, but u is the same as u here. So the larger u you have, the faster it moves. So original profile, which looks like, say, sine function, the hump would move faster than any other point. And at some point, what's going to happen? It will topple and collapse. And it's not what Russell saw in his experiment. So the KTV equation is a marvelous thing which combines both behaviors. And as a result of this dispersive effect and shock formation effect, we have solitons, which are extremely stable. I'm sure it's gonna produce your own file. Oh, no. I don't know what is looking up. I'm totally confused. Well, I'll show you one more time how a tsunami wave actually forms. So watch it one more time. You see what's happening. Huge tension is building up underwater, and then at some moment it pops up and displacing a huge amount of water. Exactly what Russell saw with that ship. And then that huge chunk of water, which you may not even see from above, but it still carries a lot of water, will produce solitons, which are actually tsunami waves. One more time, will be good.
Yeah.
Good. And next piece of history. Like I said, Ph.D. race didn't get any credit for their discovery, for the equation, and their work was dormant for 50 years. In 1959, three famous physicists, you may even, some of you may know their names. How about Fermi? Pastor Ulam are less famous, but still famous in the physics community. They studied plasma, and they did some numerical experiments, by the way, using the first computer. They tried to model plasma using a nonlinear, quadratic nonlinearity. And they used interesting kind of pendulums with not quadratic linearity. And as opposed to what they predicted what certain modes and stability. They never saw stability. It would be a recurring process, which is nothing but the soliton propagation. And it's when, and it was their work which generated some interest with this subject, although it has never been published during their lifetime either. It was a preprint which was then published in 1974, in 20 years after. But interesting is stars building up. And the order degrees equation that I showed you is nothing but the limit of the equation they tried to use to model certain plasma effects. So what they actually did, they first tried to use order degrees equation to model something. And and with enough interest generated to the equation back then, it was a revolutionary discovery by Gardner, Green, Krusman, and Muir. Unfortunately, only Muir is still alive. The previous authors died recently. And they came up with a method to solve the quadratic degrees equation, which explained everything Russell saw and whatever Fermi-Ulam pasta could not explain, their solution explained it all. And they found solution in closed form, extremely rare thing for a nonlinear equation. Almost no nonlinear equation has an explicit solution of any kind. And they found it. And they wrote a paper, 3-page paper. And it's abstract. If you just take a second and read it. If you had discovered something which would change the whole field, would you write your abstract this way? It's a very modest abstract in a paper which was 3 pages long, but it was enough to generate a lot of interest. And nowadays, what I'm going to explain next is, of course, due to Gardner, Green, Krustal, and Miura, who found a way to solve quadratic degrees equation. And they used certain machinery which was totally foreign to PDEs back then. And to review that machinery, I have to go back to get another famous discovery of approximately the same time, which is due to Schrödinger. His name, he's the father of quantum mechanics. No questions about it. He got a Nobel Prize for it, so don't have to details him. And one of his discoveries was, among others, was the Schrödinger equation. And he's of course famous for his postulates too, and his Schrödinger's cat paradox, and a few more things. And now I'm going to describe the Schrödinger equation, but we'll start with what they call Schrödinger operator, which is an operator of the second derivative with minus sign, minus multiplication by a function, which is called the potential. I'm sure if you took different courses in different equations, you would recognize in this object. Where Q is called, like I said, potential, it has some properties. For instance, it should be local, integrable, but most realistic potentials have this property. And also, I have to describe some small subtle properties that this operator certainly enjoys. And think of operator, if you don't know what it is, as a matrix in finite dimensional space. Because of course, for linear algebra, operator is nothing but a matrix. And if you recall Hermitian matrices or symmetric matrices, the Schrödinger operator has that property. It's called self-adjoint. So it's a self-adjoint operator. And you can then set up the eigenvalue problem for it, as you would do in linear algebra. And here's the equation. You see how to form it. So E here is an eigenvalue. In physics, it's called energy. And psi here is the what we call wave function. But don't worry about it, it's not that important. But this equation is important. It's called Schrödinger equation. The famous Schrödinger equation which describes quantum mechanics. And of course, everything we know about quantum mechanics or any devices which use quantum mechanics, like atomic bombs, use this equation. And the problem is that this equation cannot be solved explicitly unless Q is very simple, like a step function or a square or box type function. Otherwise, it cannot be solved explicitly. And it's, of course, a big problem. I'm sure you would try to solve such equation in your differential equations class. Or second order linear differential equations, even homogeneous with non-constant coefficients. That's a big problem. And now I have to describe its spectrum. It's, well, if I assume that my Q decays fast enough, they call it the short range, that is, the first momentum is finite, so the tails decay fast enough, faster than 1 over x squared. The decay must be faster to satisfy this condition. And then the spectrum of this operator, think of spectrum as a bunch of eigenvalues. Would have two components, discrete, which is purely negative, so all eigenvalues are negative, and they're finitely linear, like linear algebra. And but the positive spectrum is very rich. It's it fills the whole positive part of the real line, and we call such spectrum absolutely continuous. What it means for a particle to be in that zone, in the energy zone, is that it moves not in intervals, like on orbits. It can have any energy. And then, well, we have to solve the Schrödinger equation. And I'm not going to describe you how to solve it in great detail. I'm looking for a specific solution, particular solution, which has this type of asymptotics when x is large and when x is small. So either the ikx plays the role of a plane wave. So what it says is that at x going to infinity, your solution looks like a wave coming from plus infinity and then reflected from the potential. And this way would describe the part of the wave which would go through the potential. In quantum mechanics, it's possible. So there is not such a thing as impenetrable. Everything can be penetrated in quantum mechanics. And then you write your Schrödinger equation in this form, and then what you do, you just do variation parameters, thinking of the right hand side as non-homogeneous term. And if you do so, you set up an equation which you can solve by iteration numerically. And this way, you can find these coefficients, which are called reflection and transmission coefficient respectively. And those ones are very important quantities in quantum mechanics, reflection and transmission coefficients. And then you can also form what we call scattering data. Scattering data is the data that you have to know to be able to recover the potential So if you can't measure potential, usually it's not the case, but you can you can send plane waves towards it and see how they reflect. You can do all kinds of computations. You can even measure bound states, but you can't measure the potential itself. And the problem is, given what you need to know to recover the potential. And here's what you need to know. The reflection coefficient, the bound states, and and some coefficients, constants, which we call normic constants. And I'm not going to discuss in great detail what they are. They can be mysterious quantities. Their physical meaning is not that well understood, but we have to know. And then the direct scattering problem would be given potential, find this set of data, which is called scattering data. And the inverse problem would be given scattering data, reconstruct the potential. That kind of problem was of great importance right from the beginning of the boom in quantum mechanics. And we're talking about 30s, 40s, and 50s. And that problem, the inverse problem, was a particularly hard one. So they tried but could not come up with a mechanism how to recover the potential given scattering data. They didn't even know what the scattering data should be back then. And it was a breakthrough by three Russian mathematicians, Gelfand, Levitan, and Marchenko. You probably know Gelfand. He put his hands on so many different areas of mathematics, mathematical biology, and whatnot. And he died recently at the age of 93 something. And he wrote a few books. And what they found is the inverse scattering procedure, which is named after them, which goes as follows. You take the scattering data and you form the following function. You see how you form it? You take the Fourier transform of the reflection coefficient and then set up this function out of the what they call bound state data. Bound states and normal constants. And then you set up the equation, which is now called Gelfand-Marchenko. Sometimes they call it Marchenko, or sometimes even they add extra name, Ph.D. And you form the following equation. So x here is a parameter, and k is the unknown function. So it is a linear integral equation of 4k. 4k is an unknown function. F is formed by this formula. And x here is a parameter, so you have to solve it for every x. And if you do, don't ask me how to do that. It's a separate business. I know a lot about it. But we'll be able to solve it in one specific case. The potential can be recovered by this formula. Take a look. You take the k on the diagram. So you find k for x, for any x and s. You set x equal s equal x, and then you differentiate on x multiplied by 2 and you figure the potential. So it's how the famous inverse scattering problem was solved back in 1955. You see at the same time Firma, Pastu, Ulam playing around with plasma and working with KdV equation. Of course, we didn't know how to solve it, but the machinery to solve it was already produced. Well, and here's the center of the whole story. How the machinery of inverse scattering was used to solve the KdV equation. KdV equation describes water. Nowadays, it of course describes many more natural phenomena besides water. But quantum mechanics, of course, describes quantum mechanics, and not shallow water or something. And two things are going to join, to unite on this slide. So here's what Gardner, Green, Kruskal, and Miura were able to discover back in 1966. They found the following, that if given KdV equation with initial data, initial profile, you consider the initial profile as the potential for the Schrödinger operator. And then you get through the procedure which I described before, you get this scattering data made of eigen values, reflection coefficient, that we're norming constant. And then it's time evolution of the scattering data. You don't have to understand what it means, but I tell you that if you form a time-dependent scattering data from the old one by multiplying reflection coefficient by this cubic oscillatory exponential, its modulus is 1, and multiply norming constant by this exponential, they are very simple functions in time. When t is 0, s at 0 is the previous scattering data. Scattering data, s is 0. And that amazing thing is that if you consider a new Schrödinger operator, which potential is u, well, which corresponds to the potential which scattering data is given by this formula, then this u solves the KdV equation. It's a miracle. No one knows for sure why this happens. You know, when you try to fix your car, you don't have a part, and you was able to use a part from, say, a grinder to fix your car. It is usually pleasant. Here, it's a totally different scale. So that's what they call inverse scattering transform mechanism. It's of course a miracle why scattering data changes by this simple law, but it can show that it's indeed the case. So here I outlined the inverse scattering mechanism, and that's what Gardner, Green, Kruskal, Miura discovered, that this works. But apparently didn't think that it was that important at that time. It's not. It's too light here. It's taken in the same denied part in the same trip last August. You can't drive there. I was fortunate to be able to get the ticket to drive it. And now, particular solution. If you're scattering data, if you pick up your scattering data of a very simple specific form, where the reflection coefficient is 0 and there are only and there are only bound states. So such a potential is called a reflectionless, and there are some potentials in quantum mechanics. So it's a quantum mechanical system which doesn't reflect waves. They all go through it as if it was not it didn't exist. Such things do happen in quantum mechanics. Then this inverse scattering transform mechanism can be explicitly solved in closed form. So I'll discuss it a little bit later, but here's one Soliton solution, and here is one. That Q of x has the following form. It's C-squared function, yes, well, it's a good example where such weird functions are actually used. And its shape is well known. It's not a Gauss bell, but still it decays exponentially fast. And so if you take this as your initial profile, and then the solution to the KDB equation would be given by this formula. You see the difference? You get this term and nothing else. Just this extra term, which of course makes a big difference. As time goes on, what happens to the bond? It just moves to the right with no change of shape. It will just move as the whole thing with velocity, with this velocity. And of course, the height is exactly 2 kappa squared, the size of this eigenvalue. And now two Soliton solutions. That is a whole lot more interesting thing. I think I should show you a couple of times. You see how fast the one catch up this whole one and then moves forward, and you see that there is apparently almost no interaction between the two. Just as they were totally separate. But although if you look a little bit closer at this picture, you will see that actually what happens, change of phase change slightly. So the taller one would get extra boost from the slower one. Well, there are explicit formulas to describe it. And it's purely because Gardner pushed you were able to solve the KDB equation. Well, this effect which I showed you is called nonlinear superposition. And now more please. I'll be done in 5 minutes. So I'm good. How to handle n solitons? So when we have more than 2 solitons, n solitons, you can imagine the picture. Faster ones move fast and interact somehow, and it's pretty hard to describe what's going on unless you know the exact formula, and which can be derived. I'm not going to derive, I'm going to state. Very simple formula. So what we do, we form a matrix, and by n matrix, which coefficients are given by this formula where C sub n are norming constants and P sub n are bound states. So very easy formula. And then you consider what we call time-involved matrix, C. So each term of this matrix is multiplied by this exponential, which is a pretty simple object to work with. And then what you do, you add a unit matrix to it and compute the determinant of this matrix and take its second log derivative. Multiply by 2 and you get the solution to the KDB equation. Of course, if the size of the matrix is large, if you expand the determinant, it's going to look ugly. But it's in closed form. You can't expect anything better than that. And what's interesting, when time is large, each soliton behaves independently of all others. So they all go with their own velocity. Doesn't change. They don't practically don't interact. They don't merge. They don't bounce off each other, as if they were totally independent. It's the reason why they're able to transmit that much amount of information through thin fiber optic cables, because solitons don't interact. Although the equation to describe fiber optic solitons is different. It's called non-linear Schrödinger equation. Not KDV equation, but that one can be solved using the same idea, inverse Gaussian transport. Well, and they got Leroy Steele Prize in mathematics for this discovery, but only in 2006, so it was pretty recently. And their contribution was, of course, recognized. And now, what they discovered is considered to be the major breakthrough of the 19th century mathematics. The major breakthrough, which of course created a whole area of mathematics, physics, engineering, all thousands here. Well, here I'm giving you the citation from AMS event where the prize was actually awarded. So it's pretty much exactly what was said at that conference. And of course, KDV equation and equations like KDV, nonlinear Schrödinger, there's a whole zoo, large zoo of equations which are called now completely integrable equations. What they all have in common, even though they look totally differently, they can be done by inverse scattering transfer. And it's how they were able to analyze the behavior, which cannot be achieved by any numerical operators. Well, it's against the light or the pictures with dark. At the end of August, and the snow is on the ground in Denali Park. And it's Denali, it's actually 3 times as tall as on this picture. We arrived too late. The cloud moved in 1 hour before us and blocked the view. And here, yet another, it's also described by KDV equation. It's a war wave in Alaska in terminal R. And it's also a huge heap of water which disintegrates into solitons. You can see it with those ones, they are solitons. They are solitons produced by a huge initial water displacement. And it's one of the few places on Earth where you can see it that well. In most of the cases, you tides, it's tidal wave. It's just tide, high tide, low tide, nothing specifically exciting. But in terminal R, once in a month, you can see something like this. And now my main question, what do tsunami waves and quantum mechanics have in common?
Differential equations.
Well, it will be too general answer. I need something more specific. Try. The name was around. Surrender? Schrödinger equation, Schrödinger operator. That's what they have over common. It is the Schrödinger operator which allow to integrate KDV which describes tsunami waves. Thank you for your attention.
Okay. And everything they showed up there happened that you've already taught in class.
Yeah.
Yeah, complex Fourier series, even the transform.
I've ever seen.
Yeah, so that was good. Very nice. Oh, sorry. So yeah, that worked out.
This is nothing that you understand everything. It's just to have a mind.
Yeah, no, but we have
in Plasm, I know because
recognize it. We had to
I knew this potential because in Plasm we use it.
Yeah,
That's really cool. Yeah, but
Yeah.
that's good. At least you know. You see this when people say why you are solving this way. You show very clear. There are a lot of
Right,
tricks
yeah.
that you see.
definitely.
He used the word miracle. Means that
No, it did. It looked good.
not always you really, when I put a solution,
Right.
why you separate variables? It works.
Yep,
It
definitely.
works.
Well, it's how
Then
you
you
have
check.
to, what you have to do to solve the problem anyway, yeah. Well, I will see you on Monday.
You sit down there? Asked if he wanted to sit next to you or like said like Ryan might come too or whatever. And I was like, oh, I see. Like, you want to switch focus here. And I said, well, actually, no, I think I'd just like some hard teams. I don't get to talk to you every night.
No, I
I don't even know if he's going to come. He generally just kind of does I've never seen how long.
I'll be sending her this evening.
I'll be the speaker today, so I guess I'm introducing myself. I'm Jeff Bell, and I teach genetics here in the department, so this seminar is going to be a little bit out of my comfort zone. But I spent a week down in the Galapagos this summer. I took a bunch of pictures, and so we're going to take a look at it, although I am going to give you some information first here, so we need to do a little bit of science there to talk about what's going on and what's happening. We'll talk about some of that as we go along. But the Galapagos is sort of a dream trip for a biologist because it's where Darwin sort of got some of his ideas about evolution from, and a lot of the evidence for that is there. Some of which he used, some of which he was totally unaware of at the time, and there's still a bunch of things we don't understand about the species and stuff in the Galapagos. So there's still a lot of important research that can be done there. So first, just give everyone a perspective on where we're at. The Galapagos is that spot right there. Okay. So it's about 570, 600 miles off the coast of Ecuador, literally right on the equator. Okay, so the equator goes to the middle of the archipelago. So while we were there cruising around from one island to the other, we crossed the equator 6 times, back and forth on it. And so we got a little certificate and stuff at the end when we crossed the equator to the southern side. But yeah, so the islands, some of the islands are north of the equator, some are south of the equator. The equator is going to the middle of it, so it's basically right exactly on the equator. And it's very important that it is over 500 miles from the coast of South America, which makes it pretty difficult for anything to get over there to it. This is the main island, so there are a whole series of islands. They're all these volcanic islands. So this is like most of you are more familiar with the Himalayan volcanic chain. This is the same deal. There's a hot plume coming up. There's this plate moving over this called the Nazca Plate. And the islands are forming there. The plate is moving from west to east and then actually diving down underneath just lifting up the Andes Mountains. And so the older islands are over here on this side. So these are the older islands, and these over here are the newest islands that have been formed. And that has some effect on what we'll see with the animals and the plant. So we've got old islands sort of and new islands going along. And they've been out there for several million years. And it's not actually clear how long it's going on. This is sort of like maybe a sort of a stable thing. So potentially they could have been out there 10, 20 million years, but those islands are gone. So it's like new islands are forming, and then they're going in, and they're sinking down and disappearing, and then more new islands are doing it. So it's sort of like a conveyor belt thing here at this spot. So while the islands here are between 8 million and 200,000 years old, there are potentially species out here that have been living there longer than that they could have been on islands that are we can no longer see anymore because they've gone down underneath the sea. And so some of the species are actually older than any of the islands that are out there. So some of them have been there a long time. An important thing for the ecology, and it affects some of what's going on and also some of the differences that we'll see from one island to the next, has to do with where the ocean currents are hitting there. And what's going on is there's 3 different ocean currents coming in right where the Galapagos are. So there's a southern current called the Peru or the Humboldt current. There's a current coming in from the north, and then there's a current coming in along the equator, coming in from the west. And the current from the west and the south are both cold and bringing cold water and upwelling up when they get over there. And the one coming from the north is warmed up by the time it gets down there, and it's warmer water coming in from the north. And so the temperature varies of the water in particular from the east side to the west side, with the east side having warm water and the west side having much colder water. So the water temperatures vary, and that affects what we'll see on the islands by the temperature of the water affects what sort of animal life is in the water, and it affects the birds that are in the different locations depending upon where we are in the Galapagos. So the reason the Galapagos are of extreme interest to biologists and they have such an effect on Darwin was because of that isolated location and because of the fact that humans never got there. Okay? So humans did not find across that 570 miles from South America to the Galapagos, settle there, and then populate the islands, and then move from one island to the next. A couple things that really affected what goes on is there are these volcanic islands, but there are no streams. So there are no creeks, there is no running water anywhere on any of the islands. So there's no running water, there's no pools, there's 2 freshwater pools. So there's 2 spots, and we never saw them, I don't know where they are. On 2 of the islands, you know, there's a little spot where there's some sort of little freshwater pool that collects from the rainwater coming down through the volcanic rock. But that means that most of the islands have absolutely no fresh water, and even the ones that do, there'll be literally just one small pool, and that's the only fresh water on the island. So most of the islands have no fresh water. And that really affected what happened to the species that once you made it across 500 miles of ocean, you found yourself on an island with no water. Not a good deal. And so things had to be able to survive, so plants had to get there first, and then it's basically animals that made it that could get enough moisture from the plants that they ate to give them the water that they need. There is some variation on the water amount just off the altitude, so some of the islands, especially the newer islands, are tall volcanoes, and so they go up as high as 5,000 feet. And from 3,000 feet to 5,000 feet, they're able to catch an air current coming through, and there's a lot of moisture, so there's a lot of dew. So you're basically getting a lot of dew every day, and so there's enough moisture there and stuff that it affects the ecology and affects the plants that are growing. So you get very different plants up at the high elevations on the large islands that still have a big, you know, volcano there on them. The low areas along the coast are all very dry. There is no water there. They're not getting anything except when it rains, which is not a lot. So that means very few land animals, because none of the mammals could make it. So no mammals, so it's not just humans didn't make it there. No mammals made it and survived. So the islands went for all this time with no mammals whatsoever. And the only lizards and stuff that made it initially were vegetarian. So you basically wound up with a whole set of islands where all the animals, all the land animals are vegetarian. There were just no meat eaters there. There are a couple of predator birds, so a few predators did make it over there, the avian variety, but the land animals were all vegetarian initially, and they never really, they never went to the dark side. They stayed there for millions of years, just sort of walking around. You can get bigger and sort of push people around, but they didn't really fight or anything that way. But it is low diversity there because we only had only a few things could make it there, and only a few things could survive. And so, compared to most other places in the world,